Okay, the record is now on. So let's say that is the limit. So please notice that the limit itself is, just one constant, okay, one number multiplied by this always here. It's a function of a constant multiplied by square root e over fy. So what does that tell us? E is the same, right? Because regardless of the strength of the material you use, you will get the same E. But what is more important is Fy. This Fy is the denominator, meaning when you increase the Fy, your number from this formula will become less. But that will be very important because you see, when you increase the strength of the material, your material becomes stronger. So it takes more, it can take more. So it, in a way, should buckle more easily because you can compress it harder, right? And now, for this, for example, this is a typical flange local buckling for compression member with this. So for SS400, square root 56, I'm sorry, 0.56 square root E over Fy is roughly 16. So you can pretty much memorize that. And in TIS standard, for all the sections, if it is SS400, all the sections are okay. And perhaps for SM520, now we're talking about this, okay? The flange. This is, I don't remember, you have to check it. If I remember correctly, only one or two have problem, but it just so maybe the ratio, the limiting value here is 11 and you check out and you just got 10.9 or something. So you can say it's okay too, most of the time. But when when you check this, it's a web, right? For, I don't remember for sure, you need to check this. SS400, 1.49 square root E over Fy is roughly 42. I don't remember exactly. SS, I try to write the same fashion, okay? So for TIS, all the sections are okay. But this is for the web, okay? For SM500, 520, I'm sorry. Don't remember the number. Not all are okay. Must check. Okay. Now, ladies and gentlemen, there are two purposes to do the work. One is, of course, the practical purposes. When you do the real work, you may keep this in mind and go ahead and do it. But we are in this class, so therefore we must apply the academic purpose to the grading. If you do not plan to check or anything like this, you must show me that you know these limits and you have already considered them. If you don't do anything about them, okay, I am obliged to think that you do not know this. All right, so you can come back and look at the rubric here. It says that for compression member here, See? Identify relevant failure modes, local and global buckling. So you must identify them both, whether or not you calculate, if you can write proper statement about that. I'm perhaps going to say, okay, you know that, that's fine. Okay, I'm giving you this information to help you out in the future, not just for you to be reckless. Okay, and keep in mind that this is for TIS only. You may someday work with the sections of hot roll that are not made according to TIS standard. So I think it's a good habit to always check this, even though you know that it's going to be okay. Do you understand? Even though you know it's going to be okay, you must at least show me that you know it, or simply go ahead and do the calculation to complete the process. All right. Now, before you ask, what am I going to do if I run into this? No. Questions in the chat. Does the steel really? Yeah. I suppose you can say steel only has one Young's modulus, because if we let's say if you use the different material, what you have is you increase the yield, but it's still steel, so it just goes like this. So let's say SS400, it's going to yield here and then go like that. Then SF400 just keep going, and then it's going to yield there and go. So yeah, you can safely say that you can use 1E. Okay, that's the point. You should speak up, you know, don't worry, because I don't look at the screen all the time, because I use computer to host this, and therefore your question through the chat will flash on the computer screen, but I'm looking at the iPad screen while I'm lecturing. Okay, so I may have missed it in the, say, the more appropriate timing. Okay, so let's go back here. Right, so the next question I guess that you should ask would be, how am I going to do this? Now, let's say this for this class, it's going to be too much to talk about how to calculate the strength of the compression member with the local buckling issue. Okay, so let's just keep in mind that when you run into this problem, you must do something. So what is it that do something? So I'd say you either study it yourself, how you can handle it, because you now know that there is the issue of local buckling on the web, or you can just try to change the member to avoid, but just make sure that, okay, your new selection will be good economically as well. All right. So we have more cases that you can always pick your case from the table in AISC. It's available. And that is the local buckling issue. But I have to say that it is much better to use the stronger material, because most of the time SM520 will give you the smaller and therefore lighter section, and therefore better economy. This is not a big deal to take care of if you don't have. So as engineer, you should not avoid doing something simply because you don't know how to calculate this small matter of this. Okay, so that's it. Any more question on this? check. Okay, no more questions. Now, I put this on here to show you something because some folks still study the old method. This is how they calculate the critical buckling stress in the old days. They use this formula. Now we use this one. Now, then. So I can say when I was a student, when I was your age, this is what I had, you know, this horrible looking formula scared me to death. And I could never understand what's going on. I suppose they form it this way to try to facilitate the use of slide rules. You know what it is? Because back then there was no calculator. Okay, so you could not imagine calculating this function by yourself, right? It becomes impossible if you are asked to do the hand calculation by using this one. This one is okay. This one is kind of okay, but this impossible. So they try to fit the curve. Remember, this formula comes from the curve fitting from the test result. And therefore they use this because I suppose you can do it better, easier with the slide rule, but you know, it's the same thing. But this one looks horrifying, really. Okay, so you may run into some folks using this one. You can simply, hey, you can simply tell them gently, we have calculator now. I'm just going to use this one. Okay, if you want to use this, be my guest. And then if someone complains, how do you know this is correct? Ask them to use this formula and calculate and just compare the values. It come out to be pretty much the same. Okay. All right. Now, this is the fun issue. Now, this is exactly what you asked in the first hour about this. And this is what you are going to do in the class, in the project. When you consider the trust, okay? I'll try to draw the picture to my best ability. Now, you know, trust is a simple beam, right? So when I say this, it means now you know that the top chord, if it's a simple beam, top chord becomes compression member, right? And the diagonal member is going to be compression member. For some of them, going to be compression member as well. But when you consider the diagonal members, you know, the unbraced length is simply its length because it's just there. Nothing complicated, just very common. The unbraced length of the compression member in the web is just the length of the member itself, but not so for the top chord and of the truss. So let's say let's be clear about one thing. What I'm going to say from now on, I am talking about the truss that is simply supported. Okay, truss as a simple beam. So you may say that the top chord is always under compression, but you are going to have, you can have something different like this, which you're going to have in the project. You can have something like this, and the support is here, so that you know this bottom chord can become compression. Be careful, right? Oh, and Ajahn Sutat wants you to do that, so it's kind of complicated in terms of bracing. Now, you have to understand the behavior first, so that you can you see what I am going to talk about. So let's say top chord is a compression member. Okay, so now we are going to look at the top chord and see how it is braced for compression. Okay, now let's see if I look at the truss side view and this becomes my view. Okay. let's say this is my side view. Maybe I should side view. The side view, you see that whatever the web you have, when the compression member here is going to buckle in this side view, you see it can go up and down like that, right? The joint become your bracing, right? Because it cannot go up and down where the joint is, even though the member, the entire truss member can go up and down, but in terms of buckling, it has to go up and down between the joint like this. And so this is your L. Okay, are you with me?
Yes, yes.
Okay. Now, if I look at the top view, what do I see now? I see only the truss like this, correct? I don't see the web anymore, right?
Yes, yes.
So when it's gonna buckle up or down anyway once the diagonal or the webs no longer help, no longer provide the support. So if, because in the real world construction, when you build the truss, you build it in a way that this is one member. You're not going to chop it into pieces and, you know, form a joint so that you can use, you know, the truss theory and that every joint is a pin joint. Nobody does that. It's just a one long member to form this, and then you join the webs to form a truss. So without any brace, this top chord member, its entire length will become the unbraced length. Horrible, because generally truss is a very long member. But luckily, when we build the truss, we put the purlin on top of it, generally at the joint, maybe, or maybe not. Let's say if I'm going to put it like that. Let's say I can say purlins. Do you know what they are? Purlins? In Thailand, we call it pair, okay? Purlins or bracing become bracing. Bracing become bracing. So sometimes you just add some bracing in extra. So when you have the bracing, that will help prevent the movement of your compression member in this direction into that. Okay, so that becomes L according to the location of your bracing. So let's say when you look at this picture, your member, let's take a look at the bottom one first. Okay, when you look at this picture, when the buckling is going to occur up and down in the gray plane, up and down, you know, up and down in this plane. so that your member will buckle up and down like this. The joint becomes your brace point. If it's going to buckle up and down in the gray plane, it is exactly this first picture. Now it can buckle up and down, and it can also buckle out left and right. When it is going to buckle left and right out of this gray plane, we call it out of plane buckling. When it's going to move to the side like this, the webs will not help, right? It is free to go wherever it wants unless we have the lateral support here to prevent that movement. And this becomes the unbraced length. In out of plane direction, or simply this picture. You have to see it from the top view. All right. This is the unbraced length for the, say, buckling in vertical direction. In vertical. This is buckling in horizontal direction. So when it moves horizontally, it moves in and out of the plane. And when it moves vertically, this is unbraced length in plane direction. All right. So you okay? Try to think of your top chord member that can move up or down or move left or right. When it moves up or down, you know, you can say it buckles in plane, because up and down is simply in this gray plane. It's up and down in this plane. It's in this plane. But when it moves up, left or right, it's coming out of this gray plane, so it's out of plane. When it moves in plane, the joints formed by the web can help prevent the movement. But when it moves left or right, you know, the joints become useless. It cannot help. You can only get help from the true lateral support provided by either the purlin, when you put the purlin of the roof on top of the truss, or something else. Question? Hello?
Crystal clear.
Crystal clear, really? Wow, great. All right. So that's it then. This picture should help a little bit if you consider the truss, and then, you know, this, let's say if this is a major truss like that, when we have, sometimes they put the secondary truss in this location, and that becomes the brace point. And when you consider that, the out of plane buckling, that is the unbraced length. That becomes unbraced length, unbraced length for out of, oops, plane. Oh, my handwriting is gone. Let's read again. Unbrace length for out of plane buckling. Okay. Yeah, like that. That's the same picture. I'm just trying my best to give as many as illustrations as possible. Okay, and that's it. Compression member. Now it is noon time. Would you like to see one example now, or you would want to do it next time? We have plenty of time. I think it's not a bit of a worry that we cannot finish it in time. Would you like to see some example right now, or would you want to wait until next week?
How long does it take?
Pardon me, I can't hear you.
How long does it take?
I don't know. Let's say you can check this one here. Example number 3. We have member, but this is not the design just yet. It's just the investigation of the strength of one member. Okay, but can you hold off for a minute? I need to do something for my kids. Just a minute, okay? A minute or two. I'll come.